Hi, Christina. I got a really basic moment problem. See if I can help you get the concept of torque and rotation. So you might want to copy this down and pause the video so you can work along with me. But what we have here is just a beam that's attached here to a wall at A, and we have these forces acting upon it. So what I prefer to do when I'm working on a moment is I like to eliminate as many variables as possible, because who really wants to write out all of these forces? I don't. So what I prefer to do is calculate the moment at B, and then that way I eliminate the 400 newtons and the 200 newtons in the x direction, as well as the 300 newtons here. What I'll do next is choose a convention, and by convention I mean which way am I going to calculate the direction of the rotation, which way do I think this beam is going to rotate. And it doesn't matter which way you pick, because if you pick the wrong way, at worst your number is going to be negative. It'll be the correct value, but just a negative value. So I think I will calculate this going clockwise, because just how torque works, 300 newtons at this end of the beam, rotating about B would probably, we'll see, be more effective than 400 newtons this close. And I see I forgot a distance here. I'll add this in real quick. This is 3 meters. And this is 2 meters. And if you weren't able to copy down, you got 0.2 meters for the height of the beam. So, how do we write our moment? Well, we said that we're going to calculate the motion going clockwise, and we also said we're going to take it at B. And so, since torque is force times distance, we have our force 300 newtons, and it's at a distance 5 meters from B. So 5 times 300. And 300 is positive, because if we pretended that this was a lever on a pivot, and if you pushed here, you would think it would go in this direction, which is our convention, so it's positive. Now we have our next force is 400 newtons, and it's pushing down on the lever, and so if we imagine it, it would probably go this way. So since that's opposite of our convention, we'll say it's negative. Now same with torque. Torque's distance times force, so we have our force and distance, 2 meters times 400. And last, we have to shift this force up onto the same axis of our other forces, and that will be plus 0.2 times 200 newtons. And now we just have to solve. So we have 1500 minus 800 plus 40, and that gives us 700 plus 40 equals 740 newtons. That's our moment. And the most difficult part is, I think, is picking where you want your moment to be. Where does it seem like it'll be most advantageous? Which forces do you think you would like to eliminate? Now, just another thing I'd like to say, because I found a copy of your 1A problem, and one of the most difficult things that I had with moments was when you had a force vector, or a force at an angle off your beam. So say you had a force going down this way, and you can make your right triangle. Say this was at 30 degrees. And how somebody explained it to me was you separate this into its vector components. So pull this out of here. And so you would have a force going this way, a force going this way. And say you thought your rotation, it doesn't matter, but you would calculate if this being sine or cosine, this happens to be cosine of 30 degrees. That's what your trigonomic value will be for an angled force. So that's what you would use in your moment. It's easier when you have your f of x and y because you know you use cosine on x and sine on y. But in your moments, it might be a little more difficult to see that. So basically, draw a line, pretend that where it's touching is the axis, do your vector notation, and take the direction of your triangle that is most helping the rotation of the beam. I hope this helped. I think that last part was a little soppy, but when I get back, I'll make some more for you.